Hey, hi, I'm Adam Becker. As I said earlier, I am a physicist by training and science writer by trade. Currently freelance and also visiting at UC Irvine's Logic and Philosophy of Science department. And I'm going to talk today about the history of Bell's two most famous theorems in quantum foundations. With that, let's get started. So this is John Bell in about 1964, roughly the time that he wrote and published his two earliest and most well-known results in quantum foundations, Bell's theorem and the Bell-Quotient-Becker theorem. Those were his first two publications in quantum foundations. And he did both of them while he was on sabbatical, a sabbatical which he started actually out here in California, which is where this picture was taken. I think he was sort of playing a little bit at being a cowboy here. But in any event, it's kind of remarkable that these were his first two publications in quantum foundations, though it was, already about a decade into his career as a professional physicist. So I'm going to talk a little bit about how that came about. But to do that, we need to go back further than this time. What? A line just appeared on the screen for no apparent reason. I don't know how that happened. Anyway, yeah, we need to go back not to 1964, but to the beginning of Bell's days as a student in college in 1945. So this is Bell's freshman ID photo at Queen's University, Belfast. And it's kind of easy to imagine, looking at this photo, that Bell was the sort of student who might get into fights with his professors. And indeed, that's exactly what happened. In his first courses on quantum mechanics, he had a shouting match with his instructor, which he expressed some regret for that later. But he said, that he felt that the professor wasn't being entirely honest with them somehow. That he was very upset that more specific answers couldn't be given than the ones that were on offer at the time regarding questions about what was going on when nobody was looking in the quantum world. And he sort of carried this with him throughout his student days until the end of his college career around 1949. He read a book by Max Born called Natural Philosophy of Cause and Chance. And in that book, he learned of a theorem, which Born attributed to von Neumann, stating that all of the vagueness and uncertainty and whatnot that came along with the Copenhagen interpretation was inevitably part of quantum physics. And Born said that no concealed parameters could be introduced with the help of which the indeterministic description could be transformed into a deterministic one. And so Bell read this and he was very impressed that someone had actually managed to prove this. And so he said that he decided to set quantum, worries aside because he figured, that he had to get on with more practical things. Anyway, someone had proven that you couldn't do better than the Copenhagen interpretation, that you couldn't somehow find a different way to describe the quantum world. And as I said, Born ascribed this to von Neumann. And indeed, in von Neumann's famous quantum mechanics textbook, we find that von Neumann says something fairly similar to what Born said in his book. He says that you can't reinterpret quantum mechanics in a non-statistical way. You can't introduce hidden variables. Now, of course, this was wrong, but it was not widely known that this was incorrect at the time. It had already been shown to be incorrect by Greta Hermann just a couple of years after von Neumann's textbook first came out. But Greta Hermann's work on this was not widely known at the time. Part of that, I think, is that her training was not as a physicist, but as a mathematician. And so she was not, part of the community of physicists at the time. I'm not certain about that, but I believe that's correct. It's also hard to imagine that sexism wasn't at work here as well. But in any event, Hermann's result was not widely known. And so, people didn't really know who Hermann was or what she had said, whereas everybody knew who von Neumann was. He had this huge reputation at the time. Everybody partied with von Neumann. So, von Neumann's result was widely accepted as correct at the time. To get back to Bell, Bell himself couldn't go check von Neumann's proof because at the time that he was reading this, von Neumann's textbook was only available in German, and Bell didn't read or speak German. So Bell went off and, once he graduated from college, he went off and worked for the Atomic Energy Research division in the run by the UK government. And his supervisor, when he started working there, was Klaus Fuchs, who was promptly arrested a few months later for passing nuclear secrets to the Soviets. Bell said later that he had noticed that Fuchs was taking an awful lot of trips to London and he didn't know why. So after Fuchs got arrested, Bell transferred to the accelerator division and actually, ended up buying a motorcycle. Life was good. And then in 1951, he said that he saw the impossible done. He saw a pair of papers published by David Bohm, which did exactly what von Neumann and Born had said was impossible. A hidden variables theory of quantum physics that nonetheless reproduced all of the quantitative results of the theory. And so, Bell was astonished by this. And he immediately started trying to figure out how this had happened and where things had gone wrong, because he, when he read Bohm's papers, he said it was immediately obvious to him that Bohm's result was at least, quantitatively correct, that, it was the same as non-relativistic quantum mechanics. So he talked with a friend of his who knew some German and who outlined sort of the sketch of von Neumann's proof. And he said, okay, so I think I know what might be wrong with that. But then he decided to set that aside. And he set that aside for a few reasons. One of the reasons is that he wrote to Paulie and asked, what's wrong with this? Because he had been told that there was, that Bohm's ideas were not new, that de Broglie had come up with similar ideas a quarter century earlier, and that Paulie had shown that they were wrong. So he wrote to Paulie, and Paulie wrote back basically saying, yeah, no, I proved that this can't work. Don't bother with it. It's not a big deal. And Paulie, when he wrote back, by the way, it incorrectly assumed that Bell was already had his doctorate, which he did not. Yeah. So, unfortunately, Bell's letter to Paulie is lost. So all we have is the reply here from Paulie back to Bell. In any event, Bell went and read Paulie's reply to de Broglie and was unconvinced. But he saw that, there were a lot of people who believed that this couldn't possibly be right. Also, life intervened. Bell was a young man. He started working with Rudolf Peierls, who is here on the right, and started working with him on his PhD. And at the first group meeting, Pyrrell said, come talk to us about some of the things that you've been thinking about. And he said, well, I could talk about this new thing from Bohm and, quantum foundations, or I could talk about accelerators. And Pyrrell sort of looked at him and said, you should definitely talk about accelerators. And so, that also sort of persuaded him to put things aside for a while. And so he did indeed, work with Pyrrell's first PhD on quantum field theory, and actually ended up independently proving the CPT theorem for his PhD. And yeah, I mean, other stuff was going on in his life as well. He got married to Mary Bell. Here's them at their wedding, who was another physicist working with him at the Atomic Energy Research Establishment. And he also got a job a couple years after that, working at the newly established CERN, where at the opening ceremonies, he actually ended up in an elevator with Niels Bohr. And he said later on, I thought about telling him that I thought his Copenhagen interpretation was lousy, but I didn't have the nerve to do it. Now, if the elevator had gotten stuck, maybe I would have worked up the nerve, but that didn't happen. And as far as we know, it's the only time that the two of them ever crossed paths. Anyhow, so now we come back to the mid 1960s. So this is unfortunately the only picture I was able to find of Joseph Jauch, a physicist at the University of Geneva, who started working on sort of further no-go theorems to try to make von Neumann's result even more robust. And he and Bell sort of came to loggerheads a bit at in Geneva in the early 1960s. When Bell caught wind of what Jauch was working on, he said that he saw red. Because he knew that it couldn't be right. And so he talked to Jauch, and Jauch said, no, von Neumann is right, and also I am right. And also there's a further result from a guy named Andrew, oh, sorry, skipped a slide. Yeah, so yeah, Jauch and his collaborator Piron, basically ruled out stuff like Bohm. Bell was very unhappy about this because he knew that it couldn't be right. When he talked to Jauch, Jauch said that there was also another result from Andrew Gleason from a few years earlier, I believe 1957, which as a corollary also, according to him, according to Jauch, ruled out things like Bohm's theory and other hidden variable theories. So Bell was basically motivated by the idea that everyone else was wrong. And that that there was this flaw in these various theorems from von Neumann, from Jauch and Piron, from Gleason, or at least a flaw in the way that they've been understood. So he decided to see what he could do about clearing things up. But he didn't get the chance until he took that sabbatical out to California and other places here in the US in 1963 and 1964. So his first stop on that sabbatical was SLAC. This is his SLAC ID photo. He actually showed up the day after JFK was shot, which he said was the absolute worst time to show up. Which, yeah, I mean, that sounds about right. Anyway, so he sat down then finally and tried to write up his thoughts on this and really engage with von Neumann and Jauch and Piron and Gleason. And what he found when he did, as he described it later, was something that he was not very impressed with. He said that the von Neumann proof was flawed. It was, or not just flawed, but silly. He said it was not merely false, but foolish. He absolutely could not believe how badly von Neumann had screwed up here. He sat down and worked out exactly where von Neumann went wrong, and where Jauch and Piron went wrong, and how Gleason's work had been misunderstood in this context. And then he, wrote it up in the format of a review article. And he he opened the review article by saying, I've not found any analysis of what went wrong in von Neumann's proof. And like all authors of non-commissioned reviews, I think that I can restate the position with such clarity and simplicity that all previous discussions will be eclipsed. Anyway, he puts this together and he sends it off to Reviews of Modern Physics. And then a strange and unfortunate thing happens. The paper gets lost in an editor's desk for about 2 years. And then what happens is the editor finds the paper and says, well, we'd like to publish this with revisions, and sent off a letter to Bell at the return address, which was Slack. And Slack wrote back saying, we don't have any record of a Bell, because of course Bell was long gone. He had only been visiting at Slack for a few months, a couple of years earlier. And so that reply sort of stops the paper dead in its tracks. And then Bell writes to Reviews of Modern Physics saying, hey, are you planning on publishing my paper at any point? At which point an editor finally puts 2 and 2 together and says, oh, okay, I think I understand what happened here. Yeah, just send us some revisions and we'll get it published immediately. So even though Bell sent out this paper in late 1963 or early 1964, it wasn't actually published until 1966, which is why if you read it, it's very clear that it was written before Bell did his work on what came to be known as Bell's theorem. And the place where that becomes especially clear is at the end of the paper, after he's gone through and talked about what came to be known as contextuality and the Bell-KS theorem. Bell says, there's no proof that I'm aware of that says that hidden variable theories must be non-local. It would be interesting to look into that. But of course, by the time this paper was published, Bell had already published Bell's theorem, where he himself looked into that. So this question that he left open at the end of his first paper was what he decided to play around with for his next paper. So he went to the EPR setup as it was laid out by Bohm at the end of his quantum mechanics textbook from the early 50s, which is basically the version of the EPR setup that we all know and love today. It's it involves spins rather than particles entangled in momentum and position. So Bell played around with it, tried to find a model where he could make that all work locally, discovered that he could not, and then wrote up his theorem. So he sent that off. This also had a weird publication history, and I think that affected how quickly it was received by the community, as we'll see later. So he sent that off, after putting it together, to a publication called Physics Physique Physica, which was a new journal that had been put together by a couple of physicists. The idea was to sort of have a general interest physics journal available in multiple languages, covering significant results broadly of interest across the whole field. Bell sent it there rather than elsewhere because he was still on sabbatical. He was visiting places, and he didn't want to have his host institutions pay the fee that was associated with submissions at the time. So rather than asking his hosts to pay a publication fee for something, especially something outside of his usual field of research, he found this journal, which instead paid its authors, paid the people who submitted papers, and had them accepted. He said, the fee that he was paid was not very much. It was enough to buy a couple of reprints. But at least, that way he was saved the embarrassment of asking his host institution to pay the publication fee. So he gets his result submitted here, and it's picked up by one of the editors and co-founders, Philip Anderson. So Anderson looks at this and thinks, okay, this looks good. I think this looks like a really good, possible refutation of ideas like Bohm's. And so he publishes it. So Bell's theorem gets published in part because the editor responsible for looking at it completely misunderstood what Bell was talking about. So it gets published, and then things kind of go south for a little while. So in the immediate aftermath, this is what happens. First of all, Bell's first paper, which was published second in 1966, the one on contextuality, is not immediately noticed. And the other thing is, it comes out in, I believe, July 1966, and in October 1966, Koshin and Becker submit their result, which is published early the next year. And so, this becomes known as, for reasons that are actually still obscure to me, and if anybody can help me understand this, that would be great. This becomes known as the Koshin-Becker theorem, even though Bell, despite the delay, actually beat them to the punch in a lot of ways. Obviously they independently rediscovered it, and so they should get credit, but I don't really understand why this is more commonly known as the Koshin-Becker theorem rather than the Bell-Koshin-Becker theorem. In any event, I seem to be going a little fast here. I'm actually approaching the end, so I guess we'll have extra time for questions. In any event, so Koshin and Becker publish in 67. As for Bell's theorem, Physics Physique Physica goes out of print within a couple of years. It very quickly stops being what its co-founders envisioned it as being, and sort of becomes a solid state physics journal, and then just goes out of print entirely due to problems between the editors and the publishing house that they were working with. And so, by the end of the 60s, or actually by, before then, I believe it went out of print in 1968. So, within a few years, Bell's theorem is a result that was published in the back pages of an obscure, well, not the back pages, but in an obscure out of print journal. That is difficult to find. So it takes a while for it to be noticed. One of the first people to notice it is Abner Shimoni. Abner Shimoni actually ended up getting a preprint of it because Bell, I believe, was visiting Tufts at the time that he actually submitted it, or shortly thereafter. And so, because it was all still on that sabbatical year where Bell was, and where the Bells, both of them were sort of wandering around the US visiting various institutions. Shimoni, who was at MIT at the time, got a hold of this preprint. Somebody left it in his mailbox, and at first he thought it was something written by a crackpot. He said it was difficult to read. It was the ink was smeared, and then as he sort of read it more carefully, he realized, oh, this is a really significant result. But he also wasn't sure what its experimental status was, and so he asked around. He got conflicting answers about that. Some people, including Aronov, said, oh no, this has already been resolved. We already have experimental results on this. Shimoni wasn't convinced, as well he shouldn't have been. There were no experimental results at the time. And so shortly after moving to Boston University, he picked up a graduate student, Horn, and started working with him on, figuring out a way to experimentally test Bell's theorem. And he figured, they didn't have to rush, that nobody else was working on this. He was wrong. John Clauser, a graduate student at Columbia, found back issues of Physics, Physique, Physica in the library of the Goddard Space Sciences Institute in New York City, which, yes, is located directly above the Seinfeld restaurant. In any event, yeah, he found it in the back pages in that library, and actually wrote to Bell about it in early 1969. And this was the first time that Bell had received any correspondence about that paper. And so Bell wrote back saying, yeah, no, nobody's tested this. It would be good if somebody did. And so Clauser starts putting together a scheme to test it. Shimoni and Horn catch wind of it, and thus CHSH is born. And in 1972, Clauser and Friedman do the first test of Bell's theorem at Berkeley in 1972. So I am somehow already basically at the end here. So what I'll close with is question that is, I think, closely related to all of this, which is, what did Bell think his theorem meant? Because there are conflicting reports about this and some quotes of dubious sourcing about it. The best sourced and most succinct quote that I've been able to find on Bell's own opinion about Bell's theorem is the following. Bell said very shortly before his death, just a few months before he died, I don't know of any conception of locality which works with quantum mechanics, so I think we're stuck with non-locality. And this is, as I said, a very well-sourced quote, because it is actually something he said in one of the few videos we have of Bell, which is available on the CERN archive. And if anybody's interested, I'm happy to send that out. In any event, I realize I've only used half of my time, but somehow I've already reached the end. I fear that I have gone far too quickly through these slides. Because usually when I give this presentation, it goes a lot more slowly. I suspect that this is this is me speaking too quickly. Anyway, yeah, we have extra time now. Questions? And thank you for having me here today. This was a lot of fun.
Thanks, Adam. That was great. And just, yeah, please go ahead and send me that video. I'll put it on the website.
Oh yeah, absolutely. The video of Bell. Yeah, no problem.
That would be fantastic. Great. Yeah. Good. All right. So we have extra time for questions then. The next talk will be starting at 1 o'clock. So again, if you have questions, please use the hand raising tool or feel free to use the chat box.
Okay. And let me switch back to Zoom here and turn off screen sharing. That's going to take a moment because I'm not as proficient with this as I would like. Oh, wait, here we go. Stop sharing. And yeah.
In the chat box, I think, is that Jean Brickmont? Do you have a question?
Yes, I have a question. I mean, I never heard, I mean, I know the story you've been telling more or less, but I never heard about the reaction of Phil Anderson.
Yeah.
Did you write anything? Was the evidence for what is, I mean, I believe you, but what's the
Yeah,
story?
absolutely. So, so there is a book, oh my God, I'm blanking on the name of this book. There was a book by a guy named Wick.
David Wick, I know, yeah.
Yes, exactly. Yeah. Yeah, the infamous boundary. That's the name of the book. Yeah. So so Wick corresponded with Anderson when he was doing research with that for that book. And it was written correspondence, I believe over email. And so Wick sent me those letters between him and Anderson, and it's in that correspondence where Anderson says, yeah, you know, I liked this paper. You know, I was pleased by, I think his exact wording was, I was pleased by the possible refutation of Bohmism or something like that. Now, to be fair, that's like 25 years after the fact. So Anderson could have been misremembering his own reaction. yeah, it doesn't look good.
Did he realize that when he wrote this letter to Wick, did he realize that he was wrong back then, or he still believed that?
It really didn't look like he realized he was wrong. Wick certainly didn't correct him, at least not in the correspondence that Wick sent me. But yeah, it did not appear that he knew that he was wrong. I can't say for sure. I didn't ask him, and I believe Anderson passed away recently.
Of course, Gell-Mann made the same mistake. Wigner made the same mistake. Byers made the same mistake. Hawking made the same mistakes. All in my book, my book. But
absolutely,
many people have made the same mistake. But I thought Anderson would know better, because Anderson, I thought, was more independently minded mind compared to standard particle physics.
Yeah, I agree. It's surprising, but as you say, he's in very good company.
Yes.
Yeah.
or bad company.
Yes, exactly. Yeah. Distinguished company. How's that?
Okay. Yes.
Yeah.
Okay. Thank you very much.
Yeah, absolutely.
Great. So the next question I have is from David, and I also see Heather has a question also, but David, you go first.
Thanks. I'm interested in the sort of development of how people interpreted von Neumann's theorem. I haven't myself looked back to the text for some while. I don't exactly recall how von Neumann describes it, because and maybe this is just sort of anti-contrarianism, that there's a sense in which some of the criticism of that result seems to be interpreting it as doing more than or claiming to do more than it actually does, and then criticizing it for those claims. And that seems particularly likely given, as you say, the result was quite difficult to get at and access. And there's at least one reading that says, look, the most straightforward way you tell an epistemic story about quantum mechanics is you say the quantum wave function is something like the statistical mechanical wave function. There really are possessed values of the things being measured, and the measurement just tells us the answers to those things. And then furthermore, those evaluations are better way the function rules. So what is energy? Definitionally, it's p squared over 2m plus v of x. So if the system has a possessed value of p and a possessed value of x, then the possessed value of h had better be the possessed value of p squared over 2m plus v of the possessed value of x. And that's prima facie pretty reasonable way to try to make sense of quantum mechanics. And it seems pretty contentful that quantum mechanics that we discovered we can't do that, and that's the mathematical content of von Neumann's result. So I'm kind of interested where in the process does that kind of get morphed into a sort of much more thoroughgoing claim that then ends up in being the thing that they'll call silly.
Yeah, so this is a really good question, and I only have a partial answer for you. So first of all, I mean, there's the way that von Neumann describes it in his book, right? Because first of all, von Neumann's proof, von Neumann did prove something. He just didn't prove what people took him to have proven. Given the way that von Neumann talks about it in his book, it does seem that von Neumann probably took his proof to have been a bit stronger than it was, I think. It certainly seems that Born took it to be stronger than it was, and Born's book was, one of the early English language descriptions of von Neumann's result. In the world of philosophy, I also know that Norwood Russell Hansen took von Neumann's proof very seriously. It was like the cornerstone of a lot of how he thought about quantum mechanics. He talks about it over and over again in his writing, saying, look, von Neumann, one of the greatest physicists of all time, has shown that you can't do what Bohm is trying to do, and that you must accept, you must accept this to be, you must accept this result in order to engage seriously with quantum mechanics. And even Hilary Putnam, before he became aware of Bell's work and other related work, in the mid 60s, I think either shortly before or shortly after Bell's first paper, which was published second, the paper on von Neumann's proof. Either shortly before or shortly after that came out, Putnam wrote a paper where he laid out the problems with, interpretation of quantum mechanics as it stood then, and said, there are all of these problems. And, there are these solutions that would be tempting, but von Neumann's proof rules them out, including anything like what Bohm wanted to do. So I'm forced to conclude that currently there's no satisfactory interpretation of quantum mechanics. I suspect that he was influenced by Hansen in saying that. Hansen died in, I believe, 1967 in a plane crash, rather young. So I don't believe he was ever aware of Bell's work or the Cauchy-Becker theorem. But Putnam certainly changed his tune later on. Yeah.
I thought I asked the question partly because we're very familiar with the fact that Bell's theorem is very widely misinterpreted within the physics community.
Yes.
And in many respects, I find it rather more plausible that von Neumann's proof likewise gets rather widely misinterpreted in this period. I mean, after all, it's not as if von Neumann was an idiot.
Sure, yeah.
Not even as if von Neumann was a kind of calculational wonderkind who couldn't do conceptually deep stuff.
Yeah.
That doesn't automatically mean that von Neumann didn't simply make a mistake, but it's why I sort of feel some need to push back against that and at least get some sense of how the reception changes it.
Yeah, I certainly think that, I think it's very plausible that von Neumann certainly seems to have misinterpreted his own proof, but I also think that other later commentators took von Neumann's proof to mean even more than von Neumann did. Yeah. But I'm not aware of von Neumann, on the record about this, because I doubt that he considered that difference important if it existed at all. I will say that, people kept citing von Neumann and related proofs as authoritative for at least a decade, I believe more like 2 or 3 decades even, after Bell's paper came out, which, given that Greta Hermann had already shown what the problem was in 1935, that's people, citing this as saying something that it doesn't for 40, 50, maybe even 60 years after it was known not to be saying that.
Yeah, but we're 55 years after Bell's paper came out. People still cite it as ruling out
exactly. Yes. So so this is not super surprising, but yeah, I haven't traced out the exact history of how von Neumann's theorem was misinterpreted, other than the examples I gave you. I mean, I find Hansen and Putnam's, citations of it really fascinating in particular, because like Hansen leaned on it so strongly and never found out the problem. And Putnam felt that it boxed him into a corner and, would have had every reason in the world to question it. And clearly had the mathematical chops to question it, but didn't.
Great. So the next question I have is from Heather.
Hi. Yeah, thanks very much. Oh, I'm not hearing me.
Oh, I think you're muted, Heather. I can't hear you.
Can you hear me now?
Yes, I can hear you now.
Yeah.
Yes.
Still. Okay, great. Yeah. Sorry about that.
It's fine.
So yeah, my question was like very much along the same lines as David's. I was wondering really about the details of the von Neumann mistake. And it sounds like maybe to some extent it was just a overgeneralization or misinterpretation, but I was wondering if you could say just a little bit more, like in layman's terms, what the mistake was supposed to be. Yeah, so this is something that I should have reviewed more carefully before I gave this talk. But so first of all, I will say that Bell's 1966 paper on von Neumann's proof and related proofs is, I think, quite readable. I definitely used to understand this very well. I believe, and somebody please correct me if I've got this wrong, because I am sure there is somebody else here who knows this better than I do.
but basically the nature of the mistake was that von Neumann made a mistake about how hidden variables would have to correspond to expectation values of variables in the quantum theory. You know, the full, that paper that Bell wrote was basically a proof about contextuality in hidden variables, and that hidden variables theories would have to be contextual. But I don't believe that the full power of that was actually needed to go after von Neumann. I believe it was Gleason and Jauch and Perron that was needed for. For von Neumann, there was a simpler but related error at work. If I've horribly mangled that, please somebody let me know.
Jean, you have a comment in the chat box. Do you want to take this?
If I may, yes. I would like to say that it's very simple. What von Neumann assumed is that if you take two operators, even non-commuting ones, A and B, then the value, the hidden variable value of A and B must satisfy the algebraic rule that the value of the sum is the value of A plus B is the value of A plus the value of B, okay? Then you can take spin operators in the X direction, the Z direction. The value will be plus or minus 1, let's say. And then, of course, if you take the sum of the two, you know that it will be the spin in a diagonal direction if you take sigma x plus sigma z divided by square root of 2. So the value of the sum will be square root of 2 because you have to divide by square root of 2 to get, okay? And the value of A plus the value of B, value of A is plus or minus 1, must be either 2 or 0, okay? And that's, or minus 2. And that's why, you know, the theorem doesn't work. And that I think Bell made that remark, at least that's what I understand as the objection to von Neumann. I don't know who made it, but that was the mistake. I mean, the problem, I remember, I don't know who told that story, but I remember distinctly that somebody showed that proof to Einstein, and Einstein pointed out to that assumption and said, why should we make that assumption, you see? I mean, the problem, of course, in fact, if you take the Cock-Becker-Bell theorem, then of course, you assume that only for commuting observable. And then it becomes a constraint from quantum mechanics because for commuting observable, that rule must be satisfied. And so you can prove that there is no hidden variable, let's say of spin or something else, that does that kind of job. Then you can say, how does it reconcile with the Breuil-Bohm theory? Well, in the Breuil-Bohm theory, there are no such hidden variable. The only hidden variable are the position. And then from the study of the dynamics of the position, you account for the statistics of the result of measurements of operator like, you know, spin, angular momentum, etc. But there is no hidden the hidden variable, you know, the no hidden variable theorem of von Neumann is true if you restrict yourself to commuting observable, and then it becomes sensible, but still the Breuil-Bohm theory avoids that. It's it's a very confusing situation. Okay, I should stop.
Well, thank you. That was really helpful. So it seems like a kind of reasonable thing for von Neumann to have assumed in the context of so long ago. But then we see ways that you don't, it's a false assumption or one that we needn't make, like Bohm.
Yeah. I mean, it definitely seems pretty understandable that he made the mistake. I also sort of understand why Bell said that it was silly because people were taking it to mean a lot more than it actually meant. But yeah, no, I think it's a reasonable mistake to make. It just didn't mean what people thought it meant. I also want to say something, Jean, about that story that you heard about Einstein. That story's been floating around. I've heard that story. I believe that's in Wick's book as well. I have been unable to find a good source for it. I mean, Wick, I think, talks about it, but says it's second or third hand.
Yes.
As far as I can tell, like the best source I've been able to find for it is someone told it, like someone who was in the room when that happened, told it to someone else who told it to Abner Shimoni.
So something like that. Yes.
Yeah, something like that. And so I, because I haven't been able to find a better source for it, I always take that story with a little bit of a grain of salt.
Yeah, of course.
Anyway,
yeah,
but if anyone is aware of a better source, that would be great.
It's interesting to see that von Neumann considered that contribution plus the ergodic theorem as his main contribution to physics. And I think they're both irrelevant to, of course, he's a genius. That's another question.
Yes.
But when you mentioned this, the fact that this woman who refuted von Neumann's theorem was a mathematician, well, von Neumann was also a mathematician.
Well, yes.
So the sexism issue, of course, it's mostly the fame, the fact that you're so famous, but anyway.
Yeah.
Thanks a lot. So the next person I have a hand raised from Jerome. I'll get Jerome's question, and then Barry Lower has a question in the chat box. So Jerome.
Hey, so I was just wondering what Bell's ultimate thoughts then were on relativity, considering he thought that we couldn't have, locality in our fundamental theories. Sort of where he thought that relativity stood as far as fundamental physics goes.
Yeah, that's a good question. I don't have a definitive answer to that, but I have a bunch of suggestive things. So first of all, there's the fact that Bell did say in at least one, I think more like 2 or 3 of his later papers, which are collected in Speakable and Unspeakable, that many worlds or something Everettian might hold the possibility of sort of saving Lorentz invariance or locality of some kind. So there's that. There's also the fact that Bell certainly knew that non-locality and Lorentz invariance were, not exactly the same thing. I think that he didn't come out and talk about this explicitly, in part because, he knew that there was a tension there, but I don't think he would have come out and said, okay, well, the fact that there's non-locality here is like a threat to the fundamentality of relativity, right? Like I don't think he would have been willing to say something like that. And if he had been, he would have said it. That being said, he also has an interesting paper. I really like this paper in Speakable and Unspeakable. It's the only paper in Speakable and Unspeakable that's not really about quantum foundations. It's a paper called How to Teach Special Relativity, where he talks about how there are some physical situations that are arguably easier to think about in an ether theory than they are in an etherless relativity theory. Because like in the pre-Einstein but post-Lorentz ether theories, ether puts strain on things, right? And so Bell talks about this thing, which I think has come to be known as the Bell spaceship paradox, where if you think about ether as putting strain on things, it's sort of easier to see what the answer has to be. Or at least he argued it's easier to see what the answer has to be. So yeah, I mean, I think he was open to the idea that something could be, wrong or not fundamental about relativity, but I don't, I'm not aware of any definitive writing he's had on this. But yeah, I mean, he was aware of the tension, but I think as with, questions of interpretation itself, he didn't, he didn't come down in one particular side or another, right? He's often described as a partisan of Bohm's theory, but I don't think that's correct. He always said, no, Bohm's theory should be taught. I actually think there's a better case to be made that he was a partisan of spontaneous collapse theories toward the end of his life. He was very impressed with them. But even there, like, he was a little aloof about it. So I think, he was reticent to say anything about it, anything definitive.
There were a couple of comments on this discussion. Matt, you mentioned that there was a paper that Bell had written about that. Did Adam address that paper, or was this something else? Okay. Yeah, thanks, Matt. Okay. So David Wallace also had a couple of comments that are in the chat box. David, do you want to read those out loud, or do you want me to read them, or do you want to just
speak them super quickly, I suppose. I guess in terms of von Neumann's assumption, it kind of matters whether you think a hidden variable theory is supposed to say the things we call measurements of such and such classical quantity really are passively reporting possessed values of those quantities, or whether you just want an account of how that measurement process works that correctly recovers the quantum expectation values by hook or by crook. If you actually want to say, look, the system really has possessed properties of all these quantities and we're just learning what they are, it's pretty hard to avoid something like von Neumann's assumption, just because many of those properties are defined in terms of each other. If you don't want that, then then the von Neumann assumption doesn't have a lot of force, and the way is open to something like the way in which, say, the de Broglie bone theory handles measurements of quantities other than position, where there aren't possessed values of those quantities before the measurement, and yet the physics of measurement correctly recovers the observed empirical phenomenology. But from von Neumann's point of view, the very use of the word measurement is already starts to become a bit strange as soon as you move away from the assumption you're just reporting particular properties. I mean, in a version of quantum mechanics that doesn't hold on to that, like to be honest, pretty much anything we currently take seriously, then measurement doesn't really mean what it naturally means. It's not just telling you something that was already there.
I also have a finger from Carlo. Carlo?
Yeah, it's just a short comment related to the question about non-locality. I just want to point this out, that at the light of what Bell has done, the non-locality of quantum mechanics, and therefore at the light of the experiment, the non-locality of the world as we know it, it's granted, is given, is there. However, the non-locality he's talking about is a very specific definition of non-locality. There's a non-locality. Locality has a lot of meanings, and to stay with his definition is based on his notion of local variables. Quantities that are localized in space-time and have a definite value at a certain moment and a certain time. So it's not a statement about the theory, it's not a statement about reality, it's a statement about a specific interpretation, ontology associated to the theory. Which is fine, it's enormously clarifying, but it leaves, first of all, it doesn't necessarily clash with special relativity, as we know well from quantum field theory, and it leaves open the possibility that in interpretation of quantum mechanics, like many worlds, or the relational interpretation, there is not that particular non-locality. Of course, there is still sort of violation of the Bell inequalities with non-local implication that have, but these are interpretation of quantum mechanics where you don't assume that there are local variables in the sense of Bell, and therefore that particular non-locality Bell was focused upon is just definitely not there. So what I'm saying, I don't want to go into the full discussion, is that it remains true that in some sense, many world theory, many world interpretation of quantum mechanics or relation interpretation of quantum mechanics are less non-local than what Bell worried.
Thanks. So we have time for just one more question during this period. Again, just a reminder, after the third talk, we'll have a full hour for discussion about any of the talks. So if you have questions about this talk, please save them for that final hour. So we have time for one more question, hopefully a quick question. Lev?
So just one sentence, I second Carlo, there are no Bell inequalities in many world interpretation. But what I wanted to talk, I was a little disappointed that you didn't mention the work of Aharonov and Bohm, which was cited in the original 64 paper. And for when I read it and when I talked to Aronoff and once for Bohm, that they some kind of felt that this was the basis of Bell's work. They considered exactly this experiment, the Bohm type experiment, but they were close to it. They considered only orthogonal directions, so they never got never got Bell inequalities. But again, the reason why I asked to talk is because you mentioned Aronoff in a negative light. So I wanted to, he's my advisor, collaborator, so I called him now and asked if he remembers this. You mentioned that he talked to Shimoni and told him, no, there is nothing here. Anyway, what Yakira Aronoff told me now, and he's not young, but as far as I know, his memory is pretty good. And what he remembers from discussion with Avner Shimoni, that he admits the non-locality, the Bell non-locality, but there is another Bell non-locality of Aronoff-Bohm effect, and this is different. This is the only discussion which he remembers. Not that he dismissed the Bell non-locality, he just said, was trying to say that it's different from Aronoff-Bohm effect non-locality.
Yeah. Well, first, let me say, grateful and slightly terrified that you called up Aronoff just based on my talk. And also, you know, I have a lot of respect for him, and I didn't mean to paint him in a negative light. And yeah, and I'm also very grateful to the time that he gave me when I interviewed him for my book. But I should have been more clear when I talked about his interaction with Shimoni. So that was based on, I don't remember whether this is either letters of Shimoni's or an interview of Shimoni or possibly both. But what Shimoni said was that he sort of walked around for a few years with Bell's theorem rattling around in his head and was wondering about the experimental status of it. And when he went and talked to Aronoff, here, you know what? Let me get the exact quote because I've got it right here. He went and talked to Aronoff, and so he asked Aronoff whether one of Wu's experiments could be modified to test Bell's theorem, and Aronoff told him that the Wu experiment already provided such a test. And so then Shimoni said later, quote, Aronoff is a very fast thinker and a very fast talker, and I was in awe of him. I thought, he's right. Maybe he's right, but maybe he isn't right. And the more I thought of it, the less convinced I was. So what Shimoni said was that Aronoff had incorrectly pointed to a particular experiment as resolving the question of the experimental status of Bell's theorem. Now, the Wu experiment didn't do that, and the reason they didn't do that was they only looked at the perpendicular directions, which is exactly what Aronoff and Bohm talked about in their paper. So I think that's a pretty understandable mistake from Aronoff's, you know, point of view, if that's what went down after all. But yeah, no, I base that. I should have been more clear about that in my talk, but I based that on Shimoni's recollections.
Unfortunately, we cannot ask Avner now what.
Yeah.
Now Aronoff that doesn't tell that he said that the result did it already. I think, as I understand, he admits that he considered that they considered an orthogonal state, and it's not good. But yeah. Again,